Hello friends, today I am going to talk about another important distribution in probability and statistics, namely the F distribution. This distribution is derived from chi-square distribution, and this is also widely used in probability of statistics in the context of testing of hypothesis, which we will briefly mention later. So first let us get introduced with this distribution. We all know chi-square distribution by now. I hope you have gone through the introduction to chi-square distribution, both the lecture note and the video that I have uploaded. So I have got two independent chi-square random variables. So both of them are non-negative valued continuous random variables. I take their ratio. So ratio how? That x divided by n1, x has a x has degree of freedom n1, y has degree of freedom n2. Divide each random variable by its degree of freedom and then take their ratio. So then what you will get is a ratio. So n2 will come in the numerator, x into n2 divided by y into n1. So this ratio is said to follow F distribution with parameters n1 and n2. So chi-square distribution has 1 degree of freedom, but since F distribution involves two chi-square random variables, so it has 2 degree of freedom. Now F is again a non-negative valued continuous random variable because it is the ratio of two non-negative valued continuous random variable, and it has a probability density. That probability density is given by this formula. Now you can also derive it. I have skipped the derivation. How we get this formula, that is how do you get the density so obtain the density of this ratio when x and y are. So that is an exercise and that probably we will do sometime later. So anyhow, so this is a probability density function of this form. So as you can see here, in the numerator we have got y to the power n1 by 2 minus 1. So this contribution of this is coming from chi-square distribution. If you remember what was happening in chi-square distribution, and so it was, what was the formula of chi-square with n1 degree of freedom? It was some constant into y to the power n1 by 2 minus 1 e to the power minus half of y. So therefore that contribution is coming from there, and this part is coming after some mathematical operations that I will explain later. So this is also known as a beta distribution with parameter n1 by 2, n2 by 2. So F distribution is also a beta distribution, and in the denominator you see something called beta. This is a beta function that I have explained over here. So beta mn is actually gamma n divided by gamma m plus n, and in terms of factorial it is m minus 1 factorial n minus 1 factorial divided by m plus n minus 1 factorial. Now I leave it as an exercise for you to obtain what would be x to the power k expectation, that is the kth order moment. So I hope the computation will not be much trouble for you, because you will be integrating 0 to infinity this function into y to the power k. So in the what will be the change, that in the y power of y it will be n1 by 2 plus k. So then you will get another beta function, but instead of n1 you will get n1 plus k, n1 by 2 plus k, and n2 will be as it is, and then you have to do the simplification. Now here an important, so apparently you have the kth order moment, but interestingly for this distribution the moment generating function does not exist. So remember what was the definition of moment generating function, that this expectation of e to the power tx has to be finite for all values of t in some neighborhood of 0. That means you should be able to find an interval containing both negative and positive values of k for t, for which expectation of e to the power tx is finite. But you cannot find any such neighborhood of 0 for which this is finite, because for every positive value of t this is not finite. The reason for this is that, see, this integrand consists of when you are integrating over the range 0 to infinity, y to the power anything is a y is non-negative, right? So this ratio is a non-negative quantity, and e to the power ty is anyway non-negative. So the integrand over the range 0 to infinity is a non-negative function. Now when you are integrating a non-negative function, if it is a non-decreasing function at y tends to infinity, if it explodes, then that integral cannot be finite. And the fact that for any t positive e to the power ty is exploding, this you can verify by infinity form now, that this ratio will actually diverge as y tends to infinity. Therefore this indefinite integral, this improper integral cannot be finite for any positive values of t. So the moment generating function is not finite, and so we get another distribution, that is heavy tailed. This is the f distribution. So the difference from t, you remember that student's t distribution was also heavy tail, but student's t distribution there was another thing, that you could get moments only up to the order mu, where mu is the degree of freedom. Here you could get expectation of x to the power k for any k, but still it is heavy tailed. So we have now got two heavy tail distributions, namely the student's t distribution and the f distribution. And then we can have another lemma, that if I have got x1 x2 and y1 y2 independent and so suppose I have got two samples, we call them samples, x1 x2 xn and y1 y2 ym, two sets of observations from a normal distribution, and we look at the ratio of their variances, that is So this is an important lemma. So this is an important lemma which says that x1, x2, xn and y1, y2, yn are independent random variables. Then you really look what I am writing in the numerator is xi minus x bar whole square, I going from 1 to n. So this divided by n minus 1 and summation of yi square minus y bar. X bar and y bar are the means. That is summation of xi by n is x bar and summation of yi by m is y bar. So these are kind of ratio of sample variances. This follows F distribution with n1 and n1 minus 1 and m minus 1 degree of freedom. This is widely known as the F statistics and it is used to test equality of variances that I will discuss in the next slide. Okay.